March 15, 1943. Willow Run Factory, Ypsilanti, Michigan. Production manager Charles Sorensen stared at blueprints spread across his desk, calculating an impossible equation. The United States Army Air Forces needed B-24 Liberator bombers. Desperately, immediately, in quantities that seemed to defy physical reality. Sorensen's engineers told him they could build one bomber every 63 minutes once the line hit full production. Military officials nodded politely. Aircraft industry veterans laughed openly. One executive from Consolidated Aircraft, the company that designed the B-24, walked through Willow Run and delivered his assessment. "Mr. Sorensen, you automotive men don't understand aircraft manufacturing. A bomber isn't a car. You can't stamp these out like Model Ts. Each B-24 requires 313,237 rivets. Traditional riveting methods require 2 to 4 skilled workers per rivet, one person on each side of the metal. You'll never find enough skilled riveters. You'll never train them fast enough. You'll never meet your production targets." Sorensen had one response. He called an engineer from Detroit who'd been working on a solution to exactly this problem for the past 7 years. An engineer who'd invented something the aviation industry had dismissed as impractical, something they called a blind rivet. That engineer was Louis C. Huck, and his invention, ridiculed by experts as an amateur's fantasy, would help build 8,685 B-24 bombers at Willow Run. It would enable production rates that changed the course of the air war over Europe. It would prove that sometimes the most revolutionary inventions come from engineers willing to ignore conventional wisdom. This is the story of how one man's impossible fastener helped win World War II. The problem nobody wanted to solve. Let's understand what Sorensen was up against. The B-24 Liberator wasn't just another airplane. It was a 4-engine heavy bomber designed to fly deep into enemy territory, drop tons of explosives, and fight its way home through swarms of enemy fighters and walls of anti-aircraft fire. It was 67 feet long. It had a wingspan of 110 feet. It weighed 36,000 pounds empty, 65,000 pounds fully loaded. It carried a crew of 10 and mounted 10 50 caliber machine guns. It could haul 12,800 pounds of bombs. And it was made of 1,225,000 separate parts held together by 313,237 rivets. Traditional riveting, called buck riveting, worked like this. One worker on one side of the metal held a rivet gun. Another worker on the opposite side held a bucking bar against the rivet. The gun drove the rivet through pre-drilled holes in the aluminum sheets. The bucking bar formed the opposite end into a second head, creating a permanent fastener. This required skill, tremendous skill. The rivet gun operator had to apply exactly the right pressure for exactly the right duration. Too little pressure, the rivet wouldn't form properly. Too much pressure, you'd damage the aluminum skin. The bucker on the opposite side had to hold the bucking bar at precisely the correct angle. Move it a fraction of an inch, the rivet head would form incorrectly. Flinch when the gun fired, you'd ruin the joint. Both workers had to coordinate perfectly through the thunder of pneumatic guns hammering metal thousands of times per shift. The noise was deafening, the vibration constant, the margin for error non-existent. Experienced riveters developed calluses on their hands from gripping bucking bars for 10-hour shifts. They lost hearing from the constant percussion of rivet guns. They developed muscle memory that allowed them to work by feel when visibility was poor inside cramped fuselage sections. This expertise took months to develop, sometimes years. And here's the brutal mathematics of aircraft production in 1942. Each B-24 required 313,237 rivets. Each rivet required 2 to 4 skilled workers working in perfect coordination. Traditional riveting rates, approximately 4 to 6 rivets per hour per team. Do the math. One bomber required roughly 62,000 to 78,000 man-hours just for riveting. That's before installing engines, wiring, hydraulics, weapons, instruments, or any of the other 1,000 complex systems. Willow Run's goal: one bomber every 63 minutes. That's 453 bombers per month. That's 149,849 rivets per month. That's 23,600 1,500 skilled man-hours of riveting per month if you use traditional methods. Even working around the clock, Willow Run would need over 12,000 skilled riveters working simultaneously. In 1943, there weren't 12,000 skilled aircraft riveters in the entire United States. The entire pre-war aviation industry employed only a few thousand skilled riveters total. Most worked for established manufacturers like Boeing, Douglas, Consolidated, and Lockheed. These companies weren't eager to lose their best workers to Ford's new operation in Michigan. Training programs at Willow Run ran constantly. Classrooms filled with new workers learning the basics of aircraft construction. Practice stations where trainees worked on scrap metal until they developed proficiency. Supervision from experienced workers who tried to accelerate the learning curve. But you couldn't rush expertise. A mediocre riveter could install fasteners that looked acceptable but would fail under stress. Vibration from 4 massive engines, temperature cycling from -60 degrees Fahrenheit at altitude to +100 degrees on the tarmac. Metal fatigue over hundreds of flight hours. Combat damage that stressed airframe joints beyond their design limits. Every rivet had to be perfect. Lives depended on it. This was Sorensen's impossible problem, and nobody in the aviation industry wanted to hear about solutions from some automotive engineer with crazy ideas about doing rivets differently. The engineer who wouldn't quit, Louis C. Huck, was born in 1894 in upstate New York. He showed an aptitude for mechanical systems from childhood. While other boys played baseball, young Louis disassembled and reassembled clocks, studying how gears and springs work together. He enrolled at Cornell University's mechanical engineering program in 1913. Cornell had become a center for aeronautical engineering in the early 1900s. The university established a formal aeronautics curriculum in 1910, recognizing that powered flight would transform the world. Huck graduated in 1917, just as the United States entered World War I. He joined the U.S. Signal Corps, the branch responsible for military aviation at the time. He worked on aircraft maintenance and repair, learning firsthand about the challenges of keeping early aircraft operational. Those early planes were primitive by later standards. Wooden frames covered in fabric, wire bracing holding everything together, engines that failed regularly, structural failures that killed pilots. Huck saw how fastening methods affected aircraft reliability. He watched mechanics spend hours replacing damaged structural members. He observed how repeated stress caused failures at connection points. He understood that the way components were joined was as important as the components themselves. After the war, Huck worked in the emerging aviation industry. In 1928, opportunity took him to Germany. He joined Dornier Metallbauten in Friedrichshafen as a design engineer. Dornier was building flying boats, massive aircraft designed to land on water and carry passengers across oceans. The Dornier Du X, introduced in 1929, was the largest and most powerful flying boat in the world. It had a wingspan of 157 feet and could carry 100 passengers. It required hundreds of thousands of rivets holding its metal skin to the internal structure. And Huck watched the production process with growing frustration. Riveting was the bottleneck, always riveting. Skilled workers were expensive. Training new workers took too long. Production rates never met projections because riveting couldn't keep pace with other manufacturing processes. Huck started thinking about alternatives. What if you could install a rivet from one side only? What if you could eliminate the need for coordination between two workers? What if the rivet itself could generate the clamping force mechanically? The idea seemed simple. The engineering was anything but. A rivet has to create clamping force. It has to squeeze two pieces of metal together with enough pressure to create a permanent joint that won't separate under stress. Traditional rivets achieve this by forming heads on both sides of the joint. The hammering process work hardens the metal and creates tremendous clamping pressure. But if you can only access one side, how do you form that second head? How do you generate equivalent clamping force? How do you ensure the joint is as strong as a traditional rivet? Huck spent months working on the problem in his spare time. He sketched designs. He calculated stress loads. He imagined different mechanical systems. His breakthrough concept involved a mandrel, a pin that could be pulled through the rivet body. The rivet would have a hollow shank. As the mandrel pulled through, it would expand the rivet from the inside, creating mechanical clamping force. When the mandrel reached a predetermined tension, it would break off at a controlled failure point. The result? A permanently installed fastener with no access required to the back side. Huck designed prototypes. He machined test rivets in Dornier's tool shop after hours. He tested them on sample joints. He subjected them to tensile tests, shear tests, vibration tests. The results were promising, very promising, but there was a problem. Huck needed to develop production tooling, a pneumatic or hydraulic installation gun that could pull the mandrel with enough force to expand the rivet, but would automatically stop at the correct tension. This required investment, development funding, management support, and he hit a wall. Not an engineering wall, a financial wall. The year was 1929, October 1929. The stock market crashed. The Great Depression began. The golden age of civilian aviation collapsed overnight. Airlines cut routes. Manufacturers cancelled orders. Dornier stopped hiring and started laying off workers. Development programs for non-essential innovations were the first casualties. Huck's blind rivet project was shelved. He returned to the United States in 1930, carrying blueprints and prototypes, but no way to bring his invention to market. For 6 years, Huck worked various engineering jobs. He consulted for automotive companies in Detroit. He designed manufacturing equipment. He saved money. And he never stopped refining his blind rivet concept. In 1936, Louis Huck filed for a patent. U.S. Patent 2000-062-2022 was granted for his apparatus for uniting structural members. The patent described a structural blind rivet system in meticulous detail, the hollow rivet body, the mandrel with a controlled breaking point, the installation tool using hydraulic or pneumatic pressure. Huck took his patent to established rivet manufacturers. Their response was polite but dismissive. "Mr. Huck, we appreciate the innovation, but the market doesn't need this. Traditional riveting works perfectly well. The aviation industry is conservative for good reason. They won't adopt unproven fastening methods. And frankly, we don't see how this offers enough advantage to justify retooling our manufacturing processes." Aircraft manufacturers were even less interested. "Our engineers have been installing rivets the same way for 20 years. We know it works. We know it's reliable. Why would we risk switching to something new?" One Boeing engineer told Huck bluntly, "If it's not broken, we don't fix it. And buck riveting isn't broken." But Huck saw what they didn't. He understood that the aviation industry was about to face production demands beyond anything it had experienced. War was coming. Anyone paying attention to events in Europe and Asia could see it. And when war came, the limitations of traditional riveting would become critical bottlenecks. So Huck did what any engineer with an invention nobody wanted would do. He started his own company. In 1939, Huck Manufacturing Company opened in a small building on White Street by the Detroit River. The facility was modest, a few thousand square feet, basic machining equipment, a handful of employees. Louis Huck began manufacturing structural blind rivets in small batches. He refined the installation tooling. He developed quality control procedures. He tested rivets in different applications. He had no customers. He had no contracts. He had only faith that someday someone would need what he'd invented. Someday came sooner than anyone expected. December 7, 1941, Pearl Harbor, 7:48 a.m., Hawaiian time. The Japanese attack that killed 2,403 Americans and destroyed or damaged 19 U.S. Navy ships and 328 aircraft. The attack that shattered American isolationism and hurled the United States into World War II. President Franklin D. Roosevelt addressed Congress the next day. December 7, 1941, a date which will live in infamy. Congress declared war on Japan. 3 days later, Germany and Italy declared war on the United States. Suddenly, America was fighting a global war on multiple fronts, and it was desperately unprepared. The U.S. military in December 1941 ranked 17th in the world in terms of size and equipment. The Army had fewer than 200,000 soldiers. The Navy had been rebuilding since the Washington Naval Treaty limitations of the 1920s. The Army Air Corps, which would become the Army Air Forces in 1941, had fewer than 4,000 aircraft, most of them obsolete. Roosevelt called for mobilization on a scale America had never attempted. He set a production goal of 50,000 aircraft per year. Military planners calculated actual requirements. Bombers for strategic raids on Germany and Japan. Fighters to protect the bombers and achieve air superiority. Transports to move troops and supplies, reconnaissance aircraft. Training aircraft for the thousands of pilots who would need to be trained. The numbers were staggering: 60,000 aircraft in 1942, 125,000 aircraft in 1943, and those were just production targets. They didn't account for combat losses, training accidents, or normal attrition. The B-24 Liberator became a cornerstone of this massive expansion. Designed by Consolidated Aircraft in San Diego, the B-24 offered advantages over the earlier B-17 Flying Fortress. Longer range, 2,100 miles versus 2,000 for the B-17. Higher bomb load, 12,800 pounds maximum versus 8,000 for early B-17s. Lower production cost, $215,000 versus $187,000 for a B-17. The Army Air Forces wanted B-24s in huge quantities. Consolidated San Diego plant was already at capacity. A new plant in Fort Worth, Texas was under construction. Douglas Aircraft was preparing to build B-24s at their Tulsa, Oklahoma facility. But even 3 plants wouldn't be enough to meet demand. The government approached Ford Motor Company. Would Ford be willing to mass-produce B-24s using automotive manufacturing techniques? Henry Ford, 82 years old, cantankerous, and still controlling the company he'd founded, initially resisted. He was an isolationist who opposed American involvement in foreign wars. But he also understood the business opportunity, and he believed that American industrial might could be applied to aircraft production in ways the aviation industry hadn't imagined. Ford agreed, but not just to build B-24 components. Henry Ford wanted to build complete aircraft at a rate that would dwarf anything the aviation industry had achieved. He personally selected a site in Ypsilanti, Michigan, about 30 miles west of Detroit, for what would become the largest aircraft assembly plant in the world. He named it Willow Run, after Willow Run Creek that flowed through the property. The Arsenal of Democracy. Ford broke ground on the Willow Run plant in April 1941, 8 months before Pearl Harbor. The construction timeline was aggressive, impossibly aggressive by peacetime standards. Architect Albert Kahn, who had designed dozens of automotive plants for Ford, General Motors, Chrysler, and Packard, created plans for an L-shaped building that would be the largest room under one roof anywhere on Earth. The main assembly hall measured 3,200 feet long and 1,280 feet wide. Over 2.5 million square feet of floor space under a single roof. The assembly line itself would stretch for half a mile. The complex included far more than just the assembly hall. Machine shops for fabricating components, a power plant to generate electricity, a hospital for treating injured workers, an airfield with runways capable of handling fully loaded bombers, hangars for final testing and delivery, and perhaps most critically, housing for workers. The Detroit area was already crowded with war production workers. Willow Run's remote location meant workers would need transportation or housing nearby. The government authorized construction of Willow Village, a planned community with apartments, schools, shopping, and recreation facilities. At its peak, Willow Village housed 14,000 people. Ford invested $65 million of his own money into Willow Run before the government reimbursed construction costs. The federal government contributed an additional $200 million. Construction proceeded around the clock. The plant began taking shape in summer 1941. Structural steel rose from Michigan farmland. Concrete was poured in massive quantities. Electrical systems, pneumatic systems, overhead cranes, all installed while construction continued around them. By early 1942, the facility was operational. Not complete, not optimized, but capable of beginning production. The first B-24 components came off Willow Run's assembly lines in spring 1942. These were shipped to Consolidated's plant in San Diego or Douglas's plant in Tulsa for final assembly. But remote assembly proved problematic. Shipping large components across the country was slow and expensive. Quality issues emerged when parts manufactured at Willow Run didn't fit properly during final assembly elsewhere. In October 1941, Ford received permission from both Consolidated and the Army Air Forces to assemble complete Liberators at Willow Run. This changed everything. Now Ford wasn't just a component supplier, they were an aircraft manufacturer. And Charles Sorensen, Ford's production genius, was determined to prove that automotive mass production techniques could revolutionize aircraft manufacturing. The skeptics and the struggle. Charles E. Sorensen had been with Ford Motor Company since 1905. He was the man who designed the moving assembly line that made the Model T affordable for average Americans. He'd overseen construction of Ford's massive River Rouge plant, the largest integrated factory in the world. Sorensen understood mass production better than almost anyone alive. But aircraft weren't automobiles, and the differences created challenges that even Sorensen initially underestimated. An automobile in 1942 consisted of a few thousand parts. A B-24 Liberator consisted of 1,125,000 parts. An automobile was built primarily from steel stampings, bolted and welded together. A B-24 was built from aluminum sheets riveted to a complex framework of stringers, ribs, and longerons. An automobile's tolerances were measured in 1/16 of an inch. A B-24's tolerances were measured in thousandths of an inch. An automobile that developed a rattle or a leak was annoying. A B-24 that developed structural problems at 25,000 feet while being shot at by German fighters was deadly. Sorensen approached the problem methodically. He broke down the B-24 into 11 major assemblies: wings, fuselage sections, tail assembly, engine mounts, landing gear, Then he subdivided these into 69 sub-assemblies that could be manufactured in parallel. He created specialized jigs and fixtures for each sub-assembly. Traditional aircraft manufacturing involved hand-fitting parts. Sorensen wanted precision manufacturing where parts were interchangeable. The most impressive innovation was Ford's center wing section assembly. Consolidated Aircraft built each center wing section using a temporary wooden jig. The jig was built around the wing. Workers installed ribs, spars, and stringers inside the jig. They riveted the aluminum skin over the framework. Then they destroyed the jig to remove the finished wing. This process required 250 man-hours per wing section. Sorensen designed a permanent steel jig. The framework was assembled inside the jig. Overhead, cranes lifted the partially completed wing section out of the jig. The skin was installed on a separate fixture. The completed wing was moved to the final assembly line. Ford's process required 1 man-hour for the same work, a 250-to-1 improvement in productivity. But for all of Sorensen's innovations, one problem remained stubbornly resistant to improvement: riveting. 313,237 rivets per B-24, each rivet requiring skilled labor and time-consuming installation procedures. Sorensen tried everything to speed up riveting. He hired the best riveters he could find and paid premium wages. He developed intensive training programs. He experimented with different rivet gun configurations. He studied worker fatigue and adjusted shift schedules. Production improved, but not enough. Not nearly enough to reach the 1 bomber per hour target that Sorensen had promised. In early 1943, Willow Run was producing about 1 bomber per week. That was actually impressive. Going from 0 aircraft production to 1 complete 4-engine bomber every 7 days in less than a year. But it was nowhere near the production rate the Army Air Forces needed. And then someone, historians aren't entirely certain who, remembered Louis Huck and his blind rivet. The phone call that changed the war picture. A phone call in early 1943. Some Ford engineer, probably working through the weekend, trying to solve the riveting bottleneck, remembering something. A presentation at an engineering conference, an article in a technical journal, a conversation with a colleague who'd heard about this weird one-sided rivet some guy in Detroit was manufacturing. The engineer calls Huck manufacturing, explains the problem, asks if Huck's blind rivet could possibly work for aircraft structural applications. Louis Huck's response was probably something like, "I've been waiting 7 years for someone to ask that question." Within days, Huck was at Willow Run with samples of his blind rivets and the pneumatic installation tool. He met with Sorensen's engineering team. He demonstrated the installation process. The Ford engineers were skeptical. They had to be skeptical. Their aircraft were flying combat missions over Germany. Aircrew lives depended on every rivet holding under extreme stress. They couldn't gamble on an unproven technology just because it promised faster installation. So they tested. Rigorously, exhaustively, they created sample joints using Huck blind rivets. They subjected these joints to tensile testing, pulling the joint apart with increasing force until failure. Result: blind riveted joints matched or exceeded the strength of traditional riveted joints. They conducted shear testing, applying force perpendicular to the rivet axis. Result: equivalent performance. They tested vibration resistance by mounting sample panels on a shake table that simulated engine vibration over hundreds of hours. Result: no loosening, no fatigue failures. They tested temperature cycling from -60 degrees Fahrenheit to +150 degrees Fahrenheit, hundreds of cycles. Result: joints remained secure. They tested fatigue resistance, applying cyclic loads that simulated the stress of thousands of flight hours. Result: no degradation. The blind rivet worked. It actually worked. But would it work in production? Would relatively unskilled workers be able to install blind rivets consistently and correctly? Ford set up a trial installation line. They selected workers with varying experience levels. They provided basic training on the blind rivet installation tool. Then they observed as these workers installed blind rivets in actual B-24 components. The results shocked even the optimists. Workers who'd never installed a rivet before achieved acceptable installation rates after a few hours of practice. The installation process was intuitive. Position the rivet, squeeze the trigger. Hold until the mandrel snaps. Done. There was no complex coordination, no judgment calls about pressure or duration, no specialized feel that took months to develop. The tool did the work. The mandrel pulled through the rivet body. The rivet expanded mechanically. When the mandrel reached the correct tension, it broke at a pre-weakened point. If the installation was correct, you had a properly formed rivet. If something went wrong, if the rivet was misaligned or the holes weren't properly deburred, it was immediately obvious and could be corrected. Ford's quality control inspectors examined the trial installations. They used X-ray equipment to check internal rivet formation. They performed destructive testing on sample joints. The blind rivets passed every inspection. Summer 1943. Ford's engineering team made their recommendation to Charles Sorensen. Adopt the Huck blind rivet for all production B-24s. Sorensen made the decision. Install Huck blind rivets on all future Willow Run B-24s, starting immediately. Number, the transformation, the first production B-24 with Huck blind rivets, rolled off the Willow Run line in August 1943. By December 1943, every B-24 produced at Willow Run used blind rivets exclusively for appropriate applications. The impact was immediate and dramatic. Installation time per rivet dropped by 60 to 75%. Labor requirements per aircraft dropped correspondingly. Training time for new workers decreased from months to days. But the most significant impact was in workforce utilization. Willow Run employed over 42,000 workers at peak production. Approximately one-third were women. These women, immortalized in Norman Rockwell's Rosie the Riveter image, faced enormous challenges. Most had never worked in manufacturing. Many had never worked outside the home. They were taking jobs in an industry that had been exclusively male-dominated. Traditional buck riveting presented unique difficulties for women workers. Not because women couldn't do it, many women became excellent buck riveters, but because the coordination required between gun operator and bucker meant partners needed to work together for extended periods. Personality conflicts could slow production. Skill mismatches between partners created frustration. Physical strength differences sometimes created imbalances in work distribution. The blind rivet eliminated these issues. One worker, one rivet, no coordination required. Women could be trained to install blind rivets as quickly and effectively as men. The pneumatic installation tool was ergonomically designed and didn't require raw physical strength. Workers could be assigned individually rather than in teams. Production scheduling became more flexible. The democratization of aircraft manufacturing was underway. The numbers that tell the story. Let's look at Willow Run's production figures. They tell the story better than any narrative could. 1942, total production, 56 B-24 Liberators. That's an average of about one bomber every 6 to 7 days. Not impressive by later standards, but remember, Ford had never built an aircraft before. The plant was still being completed while production began. Worker training was ongoing. Supply chain issues were constant. 1943, production accelerated throughout the year, January through June, approximately 150 bombers total, averaging one every day or two. July through December, approximately 450 bombers, averaging 2 to 3 per day. Total for 1943, roughly 600 bombers. But look at what happened in November 1943, just as blind rivets became standard. November 3rd, 1943, the 1000th Willow Run B-24 rolled off the production line. Production continued accelerating. December 1943, 68 bombers produced. January 1944, 122 bombers. February 1944, 183 bombers. March 1944, 250 bombers. And then April 1944. The month everything came together. Ford workers, in 2 9-hour shifts, working 6 days per week, produced 453 B-24 Liberators in 468 hours. Let that sink in. 468 hours of production, 453 completed bombers, 1 finished bomber every 63 minutes. Charles Sorensen's impossible claim, the target that aviation industry experts had laughed at, was reality. Peak daily production in April 1944, 28 bombers in 24 hours. More than 1 bomber per hour, sustained over an entire day. May 1944, 428 bombers. June 1944, 432 bombers. Peak monthly production, 650 B-24s in a single month. The fastest sustained production rate for any heavy bomber in history. Nothing before or since has matched it. And it was possible because of innovations large and small. Sorensen's assembly line design, Ford's precision manufacturing techniques, specialized jigs and fixtures, improved worker training, and the Huck blind rivet, which eliminated the labor bottleneck that would have made these production rates impossible. The human cost of traditional methods. Consider what Willow Run would have faced without the blind rivet. 8,685 B-24s produced at Willow Run by war's end. 313,237 rivets per aircraft. That's 2,120,045 rivets total, using traditional buck riveting at 4 to 6 rivets per hour per 2-person team. That's approximately 453 million to 680 million man-hours of riveting alone. At 40 hours per week, 50 weeks per year, that's 226,000 to 340,000 worker years. Willow Run operated for approximately 3.5 years at full production, mid-1942 to early 1945. Traditional riveting would have required 64,000 to 97,000 full-time riveters working continuously. That's impossible. There weren't that many skilled riveters in America. There wasn't enough housing in Ypsilanti, Michigan for that many workers. There weren't enough rivet guns or bucking bars in existence. Without the blind rivet, Willow Run's 1 bomber per hour production rate would have remained an impossible dream. The plant might have reached production rates of 1 bomber per day, maybe 2 per day with heroic efforts. That would have meant total production of 2,500 to 3,500 B-24s instead of 8,685. That shortfall of 5,000 to 6,000 bombers would have had strategic consequences. Dabana, the strategic impact. The B-24 Liberator was the most produced American heavy bomber of World War II. 18,182 total Liberators built across all manufacturing plants. Willow Run produced 8,685 of them, 47% of total production. These aircraft flew combat missions in every theater of war: Europe, North Africa, the Mediterranean, the Pacific, China, Burma, India. In the European theater alone, B-24s flew over 200,000 combat sorties. They dropped 452,000 tons of bombs. They shot down over 5,000 enemy aircraft. But they also suffered terrible losses. Over 3,500 B-24s were shot down in combat in Europe. Thousands more were damaged. Crew casualties were horrific. The 8th Air Force alone suffered over 26,000 killed in action. The ability to replace losses quickly was critical. Germany's Luftwaffe had skilled pilots and excellent aircraft. But German aircraft production couldn't match American output. Every time the Luftwaffe shot down a B-24, America replaced it within days, often within hours. Willow Run's production line ran continuously. When a bomber was lost over Germany, another one was rolling off the assembly line in Michigan before the missing crew was even reported. This mathematical superiority, the ability to absorb losses and maintain numerical superiority, was decisive. German fighter pilot Johannes Steinhoff described facing American bomber streams in his post-war memoir. "We shot down 30, 40, sometimes 50 of their bombers in a single day. And the next day there were more. Always more. They kept coming in formations that filled the sky. We could not kill them fast enough. Our pilots were exhausted. Our aircraft needed maintenance. Our fuel supplies dwindled. But the Americans, they never stopped coming." That relentless pressure, made possible by industrial production rates that the Luftwaffe couldn't match, ground down German air defenses. By early 1944, the Luftwaffe had lost air superiority over Germany itself. American bombers struck targets in daylight. Fighter escorts went wherever the bombers went. German cities, factories, and transportation networks were systematically destroyed. The blind rivet didn't do this alone, but it was one critical link in a chain of innovations that made American air superiority possible. Davataz, the ripple effects. The blind rivet's impact extended beyond the B-24. Once Ford proved the technology worked, other aircraft manufacturers took notice. Grumman Aircraft Engineering Corporation adopted blind rivets for the F-6F Hellcat fighter. The Hellcat became the Navy's dominant carrier-based fighter in the Pacific. From its introduction in 1943 through the end of the war, the Hellcat achieved a kill ratio of 19.1 against Japanese aircraft. Over 12,000 Hellcats were produced. Peak production reached 16 aircraft per day. The Navy actually asked Grumman to slow down because production was outpacing pilot training. North American aviation used blind rivets in producing the P-51 Mustang. The Mustang, equipped with drop tanks for extended range, became the escort fighter that allowed B-24s and B-17s to strike deep into Germany with fighter protection. Douglas Aircraft adopted blind rivets for the C-47 Skytrain transport. Over 10,000 C-47s were produced. They carried paratroopers on D-Day. They supplied the airlift for Operation Market Garden. They flew the Hump over the Himalayas to supply China. General Eisenhower listed the C-47 as one of the 4 tools that won the war, alongside the Jeep, the bulldozer, and the atomic bomb. Republic Aviation used blind rivets in manufacturing the P-47 Thunderbolt. Over 15,000 P-47s were built. The rugged fighter bomber excelled in ground attack roles. By 1944, blind rivets were being used across the American aviation industry. The technology that experts had dismissed as impractical in 1936 became standard practice 8 years later. Navekobers, the enemy's calculations. German military intelligence tracked Allied production figures obsessively. They had to. Understanding Allied capabilities was essential for strategic planning. A captured German intelligence report from July 1944, found in Luftwaffe headquarters after the war, contained a stunning admission. The analyst noted, "American aircraft production has reached levels we cannot match. Ford's Willow Run facility alone produces more heavy bombers per month than our entire aircraft industry produces fighters. This production differential renders tactical victories meaningless. We destroyed 69 American heavy bombers over Germany yesterday. Today, 85 new bombers arrive to replace them. Our pilots are increasingly exhausted. We lose experienced crews faster than we can train replacements. Our aircraft factories are being bombed. Raw materials are scarce. Fuel production has been disrupted. Meanwhile, American production accelerates. Their factories operate beyond our bombing range. Their raw material supplies are unlimited. Their fuel production is unaffected. This is not a war we can win through tactical excellence alone. The mathematics are against us. That analyst understood what many German commanders refused to accept. Industrial capacity was deciding the war, and America's industrial capacity was overwhelming. The blind rivet was a tiny part of that capacity. But multiplied across millions of aircraft rivets, it represented the kind of incremental advantage that summed to decisive superiority. The workers who made it possible behind every statistic were real people. 42,000 workers at Willow Run at peak employment, working 9-hour shifts, 6 days a week, in a plant where the noise never stopped and the pressure never relented. These workers came from across America. Farm families from Michigan and Ohio who'd never seen an assembly line. Southern migrants who moved north for defense jobs. Women entering the workforce for the first time. African Americans seeking opportunities in northern industry. Recent immigrants proving their American loyalty through war work. They worked for wages that seemed good, £1.20 per hour for experienced workers in 1944, but were barely keeping pace with wartime inflation. They worked knowing their sons, brothers, and husbands were flying the bombers they built. They worked with the knowledge that a single mistake, one improperly installed rivet, could mean death for a 10-man crew. The pressure was immense, the responsibility was crushing, the pace was relentless. But they kept working, shift after shift, week after week, year after year. The blind rivet made their jobs easier. Not easy. Aircraft manufacturing was never easy, but easier. Training time decreased from months to days, which meant workers could contribute productively sooner. Installation rates increased, which meant less frustration and fewer production delays. Quality became more consistent, which meant fewer rejections and rework. One Willow Run worker, a woman named Dorothy Hayner, who later became a union organizer, recalled in a 1980s interview, "The blind rivets changed everything for us. Before that, riveting was this specialized skill that took forever to learn. You needed a partner. You had to coordinate perfectly. The noise was terrible. Your hands cramped from holding the bucking bar. With the blind rivets, I could work independently. I could set my own pace. I could be confident that when I installed a rivet correctly, it would hold. It made me feel like I was really contributing, not just assisting someone else, but doing important work myself. Multiply that experience across thousands of workers. That's the human impact of the blind rivet." The final flights, May 1945. Germany surrendered on May 7th. The war in Europe was over. Willow Run's production line stopped. The final B-24 Liberator rolled off the assembly line in late May 1945. Total production, 8,685 aircraft. These bombers had flown all over the world. Some were still conducting combat missions against Japan. Others were being converted to transports. Many were already being scrapped or sold as surplus. But their service record spoke for itself. B-24s flew over 200,000 combat sorties in Europe. They dropped 452,000 tons of bombs. They helped destroy German oil production, cutting fuel supplies to the Wehrmacht. They crippled German transportation networks. They supported the D-Day invasion and the Allied advance across Europe. In the Pacific, B-24s flew long-range missions against Japanese shipping and industrial targets. They supported MacArthur's island-hopping campaign. They helped isolate Japanese garrisons by sinking supply ships. And through it all, they were held together by millions of rivets, many of them blind rivets installed by workers who'd learned their skill in days rather than months. The legacy that endures. Louis C. Huck died in 1965 at age 71. His company, Huck International, continued operating and expanding. The original blind rivet concept evolved and improved. Modern variations include Huck bolts, two-piece lock bolts that use direct tension instead of rivet mandrels. These create joints that never loosen under vibration. They're stronger than welded joints in many applications. They install faster than threaded fasteners. Today, descendants of Huck's original 1936 patent are used in commercial aircraft. Every airliner flying uses structural blind fasteners derived from Huck's invention. Military vehicles, from trucks to tanks to naval vessels. Bridges and infrastructure, the Golden Gate Bridge retrofit used Huck fasteners. Railway equipment, locomotives and rail cars. Wind turbines, structural fasteners in tower sections. Commercial vehicles, Class 8 trucks and trailers. Electric vehicles, battery pack assemblies. Modular construction, prefabricated buildings. The principle remains the same. Single-sided installation, mechanical expansion, consistent, reliable joints. Every time you fly in a commercial aircraft, you're trusting your life to fasteners that trace their lineage back to Lewis Huck's determination to solve a problem nobody else thought needed solving. But the deeper legacy is about innovation itself. The lessons for today. Louis Huck's story offers lessons that remain relevant 8 decades later. First, recognize that the biggest problems often hide in plain sight. Everyone in aviation knew that riveting was slow and labor-intensive, but they accepted it as an inevitable limitation. Huck saw it as a problem to be solved. Second, don't let expert dismissal discourage you. The aviation industry told Huck his invention wasn't needed. Rivet manufacturers told him there was no market. Aircraft companies told him traditional methods were adequate. All of them were wrong. Third, timing matters, but preparedness matters more. Huck developed his invention in 1928. The market didn't materialize until 1943. 15 years of waiting. If he'd given up in 1935, the invention would have died. Instead, he kept refining, kept manufacturing, kept believing. When the moment came, he was ready. Fourth, sometimes revolutionary innovations look deceptively simple. A hollow rivet with a mandrel pulled through it. That's all the blind rivet is. No complex electronics, no sophisticated materials. Just clever mechanical engineering applied to an old problem. Fifth, production innovation matters as much as product innovation. The B-24 Liberator was an excellent aircraft design. But design alone didn't win the war, production did. The ability to build 18,000 bombers mattered more than building the perfect bomber. Huck's fastener was a production innovation that enabled quantity. Sixth, compound effects determine outcomes. One blind rivet saves perhaps 2 to 5 minutes compared to traditional installation. That seems trivial, but multiply by 330,237 rivets per aircraft. Multiply by 8,685 aircraft at Willow Run alone. Multiply by every other aircraft manufacturer that adopted the technology. The compound effect is millions of hours of labor saved and thousands of additional aircraft produced. Seventh, the invisible innovations often matter most. Nobody makes movies about fasteners. Children don't play with rivet guns. There are no monuments to Lewis Huck. But his invention changed history as surely as more famous weapons and technologies. The final accounting. Let's return to those numbers one last time. 313,237 rivets per B-24 Liberator. 8,685 B-24s built at Willow Run. $2,720,000, 45 rivets total. Each one installed by a worker who'd been trained in days rather than months. Each one installed by a single worker rather than a team. Each one creating a joint as strong as traditional rivets, but in a fraction of the time. Without the blind rivet, Willow Run might have produced 2,000 to 3,000 B-24s instead of 8,685. That shortfall of 5,000 to 6,000 bombers would have extended the war. Extended the war means more casualties, more cities destroyed, more lives lost. The blind rivet didn't win the war alone, but it was one of thousands of innovations, large and small, famous and obscure, that together created the industrial capacity that made Allied victory possible. Wars are won in factories as much as on battlefields. The soldiers and airmen who fought deserve honor and remembrance, but the workers who built the weapons deserve recognition too, and the engineers who made mass production possible deserve acknowledgement. Louis C. Huck spent 15 years developing an invention nobody wanted. He invested his own money to start a company with no customers. He persevered through dismissal and rejection. And when the moment came, when Charles Sorensen needed a solution to an impossible problem, Huck was ready. His blind rivet helped build the aircraft that won the air war over Europe. His invention enabled production rates that overwhelmed German industrial capacity. His persistence proved that sometimes the most important innovations are the ones that seem too simple to matter. They laughed at the blind rivet in 1936. They dismissed it in 1940. They adopted it in 1943. They depended on it in 1944. And today, nearly 90 years after Louis Huck first imagined it, the blind rivet remains fundamental to modern manufacturing. That's how you change the world. Not by inventing something flashy and obvious, but by solving real problems in ways that compound over time. By persisting when experts say it won't work. By being ready when the moment arrives. 8,685 B-24 Liberators, 2 billion rivets. One engineer who refused to quit. They laughed at the blind rivet until it helped win the war, 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 helped win